Close your eyes and imagine the universe as a quiet ocean, vast, endless, and stretching in every direction. In this ocean, most stars sparkle like lanterns, their light carried across unimaginable distances to reach us. Yet hidden among them are places where light itself is swallowed whole, places so strange that even time begins to hesitate. These are black holes, silent mysteries that have captured both the fear and wonder of human imagination. Tonight, let us drift together through the stories of these invisible giants, letting curiosity guide us as softly as the tide of the cosmos itself. The strange silence of the universe. When you look into the night sky, the first thing you notice is light. Stars, planets, galaxies, all sending their brilliance across space. But the universe is not only about what we see, it is also about what remains unseen, the gaps, the shadows, the strange silence between flickering lights. Black holes live in this silence, not glowing, not shouting for attention, but quietly pulling on everything near them. It is as if the universe keeps a few secrets tucked away in its darkest corners, waiting for us to lean in and listen. Astronomers first began to wonder about these silences when they saw stars behaving oddly. Some stars moved as though an invisible partner tugged at them. They circled nothing, as if dancing with a ghost. What could cause such movement? The idea was almost unthinkable at the time, something massive and heavy enough to drag a star around, yet completely invisible. In the stillness of the universe, these hidden giants left only whispers of their presence, little signs for those paying attention. There is a strange comfort in silence too. Think of a quiet night, when all you hear is your own breathing. The silence does not feel empty, it feels alive, as though something larger than you is listening. That is the silence of the universe around black holes. It is not emptiness, but a heavy hush. And in that hush you feel the weight of something both terrifying and deeply beautiful. We call them black holes because they let nothing escape, not even light. But perhaps the better name would be something like cosmic shadows, because they are not objects in the way we imagine stars or planets. They are regions, thresholds, places where the rules of space and time twist into new shapes. When we speak of them, it feels like telling a story about a door in the fabric of the universe itself. And as we sit with this silence, we begin to sense the first whispers of these invisible giants, subtle signs that something extraordinary lurks behind the stillness of the night sky. The first whispers of invisible giants. Before anyone could ever prove black holes existed, there were clues, faint suggestions in the way stars shifted or how starlight bent in unexpected arcs. It was as if the universe left breadcrumbs for the curious to follow. These whispers were not loud discoveries, but quiet mysteries, tiny anomalies in the data that did not quite make sense. To most, they could have been errors. To a few, they were the beginnings of a deeper truth. Imagine a giant unseen hand tugging gently on a star, pulling it into a circle. You cannot see the hand itself, but you notice the way the star obeys. This is how astronomers first glimpsed the influence of black holes, not by seeing them directly, but by witnessing their effect on others, a hidden force so powerful that even massive stars bowed to it, left traces too strong to ignore. The whispers became impossible to dismiss. For centuries, our ancestors believed the heavens were a grand clockwork, every star fixed in place. The discovery of invisible forces challenged that comfort. Suddenly, the universe was no longer only about shining stars, but also about unseen powers lurking behind them. These whispers invited us to imagine that reality was stranger than our eyes could perceive. And isn't that a thrilling, if slightly unsettling thought? To scientists, Whispers become invitations. Each small clue about black holes drew us closer, like a candle guiding travelers in the dark. Every wobble in a star's orbit, every flicker in its light, every unexplained tug was a sign that something immense was hiding nearby. The giants did not roar, they did not announce themselves, they whispered, and humanity leaned closer, ears pressed against the cosmos. And once you start hearing whispers, you cannot help but follow them deeper until silence itself begins to take shape as a presence in the dark. Gravity's secret grip in the dark. Gravity is a quiet force. You never see it, but you feel it every moment you stand, every time you drop something, every time Earth holds you in her embrace. In space, gravity becomes the sculptor of everything. It pulls stars into galaxies, it binds planets to suns, it bends the paths of comets. And in the darkest regions, gravity becomes something even more mysterious, an invisible grip so strong that not even light can slip away. The story of black holes begins with gravity's determination. When a star grows old, its own weight presses inward. Normally, heat and light push back, keeping the star in balance. But what happens when the star grows too heavy, or its fuel runs out? The balance tips and gravity wins. The star begins to collapse in on itself, folding tighter and tighter until there is no space left to fold. Gravity has clenched its fist. It is not a violent explosion we imagine here, but rather a slow tightening like a hand closing around something fragile. In that tightening, matter itself is crushed into an impossibly small space. The result is no ordinary star, no ordinary object. It is something new, a place where gravity is absolute, where nothing has the strength to resist its pull. In this unseen grip, black holes are born. Think of it as the universe showing us just how far gravity can go. On Earth we trust gravity like an old friend, but in the heart of a black hole, gravity becomes something unfamiliar. It is still the same force, but taken to its extreme, where it rules with complete authority. The same gentle friend that holds our feet to the ground becomes an all-powerful ruler in these regions of space. And once gravity closes its grip fully, we find ourselves face to face with one of the strangest places in the cosmos, the point where collapse bends even time itself. When a star grows too heavy to hold itself, stars are born with a balance. Deep inside, nuclear fire burns, pushing outward, while gravity pulls inward. This tug-of-war can last for billions of years, creating the light that warms planets and seeds life. But when the fuel runs low, the balance falters. For smaller stars, the collapse leads to quiet endings, white dwarfs or neutron stars. But when a star is truly massive, heavier than millions of Earths, gravity refuses to be gentle. It drags everything inward, unstoppable. In those final moments, the star's outer layers may flare outward in a supernova, a spectacular farewell. Yet beneath that explosion, its core collapses further, shrinking past every limit. The heat and light can no longer hold it up. The star folds into itself like paper crushed into a ball. Only the ball is smaller than we can even imagine. From brilliance and fire, it becomes invisible, silent, yet more powerful than ever before. It is a humbling truth. The same stars that give life with their light also carry within them the seeds of darkness. When they grow too heavy, when they can no longer support their own glow, they give birth to something completely different. The universe transforms them not into ashes, but into cosmic abysses. They become black holes, reminders that endings are not always quiet, but can reshape reality itself. If you pause and think, there's something almost human about it. Too much weight, too much burden, and collapse follows. Stars, like us, can only hold so much before surrendering to forces greater than themselves. Yet in that surrender, something new is born. Perhaps that is why black holes fascinate us, because they mirror the delicate balance of strength and collapse that we know in our own lives. And in the deepest moment of collapse, when nothing can resist, the star's death gives way to a place where even time itself begins to bend. The collapse that bends time itself. Black holes are not just about crushing matter, they are about twisting time. Imagine standing near one, though in reality no one could survive it, and feeling seconds stretch into hours. To an observer far away, you would appear to move slower, as though caught in a slow-motion film. Time itself bends under the weight of the collapse. It is not a trick of perception, but a true bending of reality. Einstein's theory of relativity first hinted at this. Gravity, he explained, does not simply pull, it curves the fabric of space and time. Near a black hole, this curvature becomes extreme. It is like rolling a marble on a flat sheet and then dropping it into a deep well. The marble cannot escape and the sheet itself is distorted. Black holes create wells so deep that even light, the fastest traveler in the universe, cannot climb out. To imagine time bending is unsettling. We live, trusting that seconds are steady, that minutes always march forward. But near a black hole, the march slows to a crawl. It means the universe is not uniform, not absolute. Time is flexible, stretched like a thread. And if time is not fixed, then what does that say about the nature of existence itself? The collapse of a star, then, is more than just a transformation of matter. It is a transformation of time, of reality, of the rules we thought were unbreakable. It shows us that the universe has layers deeper than we first believed. Beneath the glitter of stars lies a stranger truth, one that humbles and inspires at the same time, a place where escape becomes impossible. At the heart of a black hole lies a truth both simple and unsettling. Once you cross a certain invisible line, nothing, no matter how fast, how bright, how determined, can escape. Not even light. Imagine a valley so deep that every attempt to climb out only pulls you back faster. That is the essence of a black hole. It is not a prison made of walls, but of gravity itself, woven so tightly that freedom becomes a forgotten word. This idea alone reshaped how we think about the universe. To humans, escape is always possible, whether by climbing, by running, or even by dreaming. But black holes present us with a place where the concept of escape ends entirely. It is a reminder that the cosmos holds boundaries not of stone but of laws, and once those laws are set, they cannot be broken. A star, a planet, even light itself, all become trapped the moment they fall too close. To picture it, imagine a river flowing faster and faster toward a waterfall. Far upstream, a fish can swim freely. Nearer, it must work harder. And once it crosses the very edge, no strength in its body can fight the pull of the fall. That edge is what defines a black hole. It is not the hole itself, but the boundary beyond which return is impossible. A cosmic waterfall, silent, invisible, yet absolute. Scientists call this point the escape velocity. On Earth, you would need a rocket moving 11 kilometers per second to break free of gravity. At the surface of the Sun, you would need 600 kilometers per second. At a black hole's edge, you would need to move faster than light itself. But since nothing in the universe travels faster than light, nothing escapes. The rule is not complicated, it is simply unbending. And so we arrive at a place in the universe where escape ceases to exist, not because of walls or cages, but because the very rules of reality fold in on themselves, and just beyond this invisible border lies a realm of even stranger wonders. The invisible boundary called the event horizon. The edge of a black hole has a name both poetic and precise, the event horizon. It is not a surface you can touch, it is not a line painted in space, It is a horizon in the truest sense, a limit to what can be seen, a line beyond which events can no longer reach us. What happens inside remains hidden forever. The story beyond the horizon is swallowed whole. For an outside observer, something falling into a black hole never quite crosses the line. You would see it slow down, fading, stretching, becoming dimmer until it disappears. Yet for the object itself, the crossing would feel swift, with no sign of hesitation. Two realities at once, one for the falling traveller, another for those watching far away. The horizon bends not just light, but our very sense of time and truth. There's something almost mythical about it. Ancient cultures spoke of gateways between worlds, thresholds you cannot return from. The event horizon is a modern echo of those old myths. Step across, and your story no longer belongs to the universe outside. It belongs to the black hole alone. It is as if reality itself draws a curtain and says, "No further shall your tale be told." And yet, this horizon is not absolute silence. Near it, matter and energy swirl violently, creating some of the brightest phenomena in the universe. Paradoxically, the darkest place we know is surrounded by light. Jets of particles, bursts of energy, the frantic screams of matter before it falls. The horizon is a quiet border, but it is framed by chaos and brilliance, a contrast almost too beautiful to ignore. To speak of the event horizon is to speak of the line between the known and the unknowable. It is the edge of mystery itself. And just beyond it, light begins to behave in ways that challenge every certainty we once had. Light trapped in eternal circles. Near a black hole, light does not move in straight lines. Instead, it bends, curves, and sometimes becomes trapped in perfect loops. There exists a region called the photon sphere, a place where light itself orbits the black hole, circling endlessly like a moth caught in an invisible whirlpool. It is one of the strangest predictions of physics. Light, which we think of as free and untouchable, chained into eternal circles. Picture beams of starlight wandering through space, only to pass too close to a black hole. Instead of continuing forward, they are bent around, sometimes spiraling again and again, caught in the grip of gravity's perfect curve. To an observer, this creates illusions, rings of light, distorted images, the same star seen multiple times. The black hole does not glow, but it paints pictures with the light it bends. A silent artist working with borrowed brushstrokes. These light rings are not just theoretical. In 2019, the first true image of a black hole revealed a glowing halo around a dark center, the shadow of the black hole surrounded by bent light from behind it. For the first time, we saw not the hole itself, but the light enslaved by it. Humanity had captured a portrait of the cosmos at its most haunting. And in that image, silence itself seemed to speak. The photon sphere is unstable. Light trapped there cannot stay forever. The tiniest disturbance sends it spiraling inward or fleeing outward. Yet the idea of light caught in a dance with darkness remains one of the most poetic truths in science. It shows us that black holes do not merely consume, they sculpt, they shape, they transform what passes near them into visions of eerie beauty. And as light circles the abyss, time itself begins to circle too, stretching and slowing until even seconds hesitate on the edge of forever. Time slowing as you approach the edge. Time is the one constant we trust, ticking forward steadily whether we notice or not. Yet, near a black hole, time loses its firmness. The closer you approach, the slower it passes compared to those far away. If you watched a clock falling toward the horizon, you would see its tick slow, its seconds drawn out until it seemed to stop altogether. The black hole does not just swallow matter, it stretches time into stillness. This phenomenon, called time dilation, is not fantasy but fact. born from Einstein's theory of relativity. Gravity curves not only space, but time itself. Near Earth, the effect is tiny. Satellites must adjust for it, but we never notice. Near a black hole, however, the effect becomes profound. Time slows to a crawl, a reminder that our seconds are not universal, but local. Time is not a river flowing evenly, but a stream that bends around the obstacles of gravity. Think of the implications. A traveler falling into a black hole might experience only minutes passing, while to the outside universe, millions of years could go by. In this way, black holes become not just prisons of matter, but strange one-way windows into the future. To step close is to step outside the rhythm of the universe into a distorted beat of reality itself. And yet, this slowing of time is not only terrifying, it is also strangely beautiful. Imagine a place where the last moment of a star is stretched into eternity, where light from its final scream lingers forever at the edge. The black hole turns endings into infinite pauses, preserving them in cosmic amber. There is a strange poetry in this, the universe holding on to farewells a little longer than it should. And beyond that pause, at the very center of it all, lies the most mysterious heart of all, the singularity, where even our best ideas about time and space collapse into silence. The point of no return. The phrase point of no return is often used in human stories, moments when choices cannot be undone. In black holes, this phrase becomes literal. The event horizon marks it, but the singularity at the core defines it. Once inside, all paths lead inward, toward a point where density becomes infinite, where space and time themselves break apart. It is not just a place we cannot return from, it is a place where the very meaning of return dissolves. At the singularity, our equations falter. Physics, so reliable elsewhere, fails to describe what happens. Matter is compressed into an infinitely small point, a concept beyond imagination. What does it mean for something to have no size but infinite mass? It is not simply strange, it is impossible to picture. And yet, the universe insists such places exist. The singularity is less a destination than a question mark carved into the fabric of reality. For a traveler crossing the horizon, the singularity is inevitable. No matter the path, no matter the strength, all roads curve toward it. It is as if space itself conspires to guide you inward. In human terms, it feels like fate, an unavoidable conclusion written into the very shape of the cosmos. This inevitability is both terrifying and humbling, reminding us how small we are before the weight of universal law. And yet the singularity is also a place of possibility. Because our laws break down there, it is also where new physics might be waiting, answers to mysteries we cannot yet grasp. Perhaps within that impossibility lies a clue about how the universe began, or how it might someday end. Perhaps in the silence of the singularity is the key to understanding everything else. And so at the end of this path, we arrive at the center of darkness itself, a place where escape is forgotten, light is bent, time slows, and space itself collapses into mystery. The singularity at the center. At the very heart of a black hole lies the singularity, a place where matter is crushed into something smaller than imagination allows. It is not a surface you can touch, nor a point you can see. It is the end of our equations, the place where physics falters and whispers that it can go no further. The singularity is a riddle written into the fabric of the universe. To scientists, this singularity is both thrilling and frustrating. Thrilling because it suggests there are deeper laws still waiting to be uncovered. Frustrating because our current understanding cannot fully describe it. Imagine a book with missing pages. Every clue builds tension, but the ending is torn out. That is what the singularity feels like, an unfinished story hidden inside the darkest places of the cosmos. We often picture black holes as cosmic monsters, but the singularity reminds us they are also mysteries. This point may hold secrets about the birth of the universe itself, for in many ways the singularity at a black hole's heart resembles the conditions of the Big Bang. Infinite density, timelessness, space folded into nothingness. It is as if black holes are cosmic echoes of creation. But the singularity is not just about beginnings, it is also about endings. Anything that falls within a black hole is destined to meet it. The path is inescapable. The singularity does not choose, it simply waits. In its silence there is no malice, only inevitability. The universe itself curves toward it as though fate is not a word but a shape. And yet even in this finality, the singularity sparks possibility. It may be the gateway to new physics, a place where our current knowledge crumbles to make way for something grander. And so from the heart of darkness, wonder is born, matter crushed into pure mystery. When we speak of matter inside a black hole, we step into strangeness. The atoms, the particles, the familiar building blocks of reality, all are crushed beyond recognition. The structure of matter that we know on Earth cannot survive the pressure. Electrons and protons, which make up everything from mountains to oceans, are pressed into a state so unfamiliar that we call it pure mystery. Matter ceases to behave like matter. This crushing is not destruction in the usual sense. The particles are not burned away or scattered. Instead, they are compressed so tightly that their individual identities disappear. Imagine folding paper endlessly until it is no longer paper at all, just a lump of unimaginable density. That is what happens to matter at the center of a black hole. The ordinary becomes unrecognizable, yet still exists. And here is the strange thought. Though we cannot describe the exact state of this crushed matter, we can measure its effects. The black hole still has mass, still exerts gravity, still bends space. Whatever happens inside, it leaves fingerprints on the universe outside. Mystery it may be, but its influence is undeniable. It is like listening to music from behind a wall. You cannot see the instrument, but you feel the vibration in your bones. To call this pure mystery is not an admission of defeat, but an invitation. Science thrives on mysteries, on the gaps in our understanding that draw us forward. What is matter inside a black hole? Is it a new state of physics? Is it energy beyond form? Or is it something we do not yet have words for? Each guess opens new doors of thought. So while matter may vanish as we know it, its mystery remains, heavy and enduring. And from that crushing, we glimpse the edges of truth not yet revealed. Why physics breaks down here? The singularity is more than a puzzle. It is a breaking point. Our best theories, so reliable elsewhere, collide at its edge and crumble. General relativity describes gravity perfectly across the cosmos. Quantum mechanics rules the tiny world of particles with stunning precision. Yet when we try to use both at once to describe a black hole's core, they refuse to fit. It is as though two languages, each beautiful, suddenly clash into noise. This breakdown is not failure but revelation. It shows us that neither theory is complete on its own. The singularity is where they meet and where they contradict. Relativity says space and time curve infinitely. Quantum mechanics says infinities cannot exist. Both cannot be true, and yet both work everywhere else. The singularity laughs at this conflict, forcing us to admit there must be a higher truth we do not yet see. Think of it like watching two maps overlap. One describes rivers and valleys, the other marks cities and roads. Both are correct, but when laid together they blur and confuse. Something more complete is needed. For physics, that missing map may be a theory of quantum gravity, a unified law that explains both the vast and the tiny. Black holes in their silence may be the teachers that guide us to it. The breakdown at the singularity is frustrating, yes, but also profoundly hopeful. Because whenever knowledge fails, it means we are brushing against the edge of discovery. The singularity does not hide from us, it beckons, daring us to keep asking questions. The collapse of physics is not an end, but the doorway to a greater science waiting in the dark. And so black holes are not only destroyers, they are also reminders that our knowledge is fragile and that beyond its limits lies a larger horizon of truth. The idea of infinite density. The word infinite is both awe-inspiring and unsettling. To imagine infinite density is to imagine mass without space, weight without volume, existence compressed beyond all boundaries. At the singularity, this is what our equations predict. Matter collapsed into a point of zero size, yet with enormous mass. It is an idea almost too large for the human mind to hold, and yet it stands at the center of every black hole. But here is the twist. Physicists suspect infinity is not real. Instead, infinity is a sign that our current mathematics is incomplete. When a calculator flashes error, it is not that numbers have failed, but that the question itself goes beyond the system. The singularity's infinite density may be the universe's way of flashing error, reminding us that a new framework is needed to explain what truly happens inside. Still, the image of infinite density lingers in our imagination. It represents the ultimate compression, the final surrender of matter to gravity. It suggests a place where everything familiar, solids, liquids, gases, even atoms, loses its identity. It is a concept that stretches not only science but also philosophy, forcing us to ask, can existence itself be squeezed into a point? For some, the idea sparks fear. For others, it sparks wonder. Because if matter can collapse into infinity, what does that say about beginnings? Could the universe itself have started from such a point? Perhaps the singularity of a black hole and the singularity of the Big Bang are not strangers, but reflections of one another, two infinities whispering across time. And as we sit with this haunting thought, the picture grows larger. For black holes do not only bend matter into impossibility, they also bend space around them like rubber stretched to its breaking point. How black holes stretch space like rubber. Imagine space not as emptiness but as fabric, something that can bend, stretch, and ripple. Black holes take this fabric and pull it into shapes almost beyond recognition. Around them, space curves steeply like a sheet, pulled tight and pressed down by a heavy stone. Anything that rolls nearby is drawn inward, and the closer you get, the deeper the well becomes until escape is no longer possible. And this is not just metaphor, it is reality. Gravity, as Einstein revealed, is not a force pulling at objects, but the warping of space itself. The Earth orbits the Sun not because the Sun pulls it with an invisible hand, but because the Sun bends space around it, and Earth simply follows the curve. A black hole, with its immense mass, takes this principle to its extreme. It turns the gentle dimples of stars into bottomless pits. Visualizing this helps. Picture a trampoline with a heavy ball placed in its center. Smaller balls roll toward it, spiraling in as the fabric dips. Now imagine a weight so heavy it tears through the fabric entirely. That tear, that bottomless hole, is the closest image we have of how black holes stretch space. They do not sit in space, they reshape it entirely. The effect is not limited to matter. Even light, which usually travels straight, follows the curves of space. Around black holes, those curves are so steep that light circles or falls inward. In this way, black holes reveal the flexibility of space itself. What we once thought was empty turns out to be alive, elastic, responsive to mass and energy. And as this stretched fabric ripples around black holes, it leads us naturally to another wonder, the bending of starlight itself, creating visions of cosmic beauty called gravitational lensing. Space-time as a living fabric. We often think of space as nothing, a vast emptiness, but black holes remind us it is more like fabric, alive with tension and curves. Imagine a sheet stretched across a frame. Place a marble on it and the sheet dips. Place a planet and the dip becomes deeper. Place a black hole and the sheet is pulled almost endlessly down. Space is not still. It bends, it stretches, it responds to mass like fabric under weight. Einstein's great insight was that time and space are not separate. They are woven together into one fabric, space-time. Black holes do not only stretch where you might walk, they also stretch the very seconds you live through. Space and time flex as one. The ticking of a clock and the path of a star are both guided by the same invisible fabric. Around a black hole, that fabric becomes almost unrecognizable, pulled to its limits. If you picture space-time as a rubber sheet, then matter is the weight that bends it. But unlike ordinary fabric, space-time does not tear easily. It flows, it curves, it holds. Black holes show us the most extreme example of this flow. Their presence is so heavy that the fabric of space-time dips into wells deeper than our minds can fully picture. And in those wells, everything else, matter, energy, even light, must follow the curves drawn around them. This is why black holes are not like ordinary objects. They are not chunks of matter in space. They are distortions of space itself. They are geometry made real, a fold in the map of the universe. That fold shapes not only their immediate surroundings, but also the galaxies that host them. A single tear in fabric may ripple across the whole cloth. In the same way, black holes ripple across the cosmic weave. And as this living fabric bends, something remarkable happens. The very starlight that should pass in straight lines is caught and twisted, turning black holes into silent lenses that show us the hidden beauty of the universe, the bending of starlight around darkness. One of the most haunting sights near a black hole is the way it bends light itself. Imagine a distant star shining behind one. Instead of disappearing, its light curves around the darkness and reaches us anyway, appearing in strange arcs or even multiple images of the same star. This bending is not an illusion. It is the path light must take when space itself is curved. The black hole becomes an artist, reshaping light into cosmic patterns. Astronomers call this phenomenon gravitational lensing. It is as though the black hole acts as a giant magnifying glass, bending and focusing light that passes nearby. Through this effect, we can see galaxies otherwise hidden behind others, stretched into arcs, multiplied into rings. The darkness reveals light by bending it, a paradox that feels almost poetic. The place that swallows light also reveals it in unexpected ways. To our eyes, the images produced by lensing look surreal. A single galaxy stretched into a curve, a quasar appearing 4 times around a dark center, circles of glowing fire known as Einstein rings. These are not tricks of imagination, but the universe showing us its true geometry. Space itself becomes the painter, and light becomes its paint. Black holes, silent and invisible, leave behind artwork that astonishes even the most cautious of scientists. The bending of starlight does more than inspire, it teaches. By studying these distorted images, astronomers can measure the mass of black holes and even map the distribution of dark matter in the universe. The effect is not just beautiful, it is a tool, a window into the unseen. In the distortion of light, we discover the hidden weight of the cosmos. And so, through this bending, black holes remind us that seeing is not always believing. Light may lie, images may twist, but the deeper truth remains. What lies unseen still shapes what we see. a cosmic magnifying glass we call lensing. Gravitational lensing is not confined to black holes alone, but they create its most dramatic forms. Imagine peering through a lens not made of glass, but of warped space-time. A black hole sitting between us and a galaxy far behind it can bend the light so perfectly that the galaxy appears magnified. It is as if the universe itself hands us a telescope, carved not by human hands but by gravity. This natural magnifying glass has given us glimpses of the farthest galaxies ever seen, shining from billions of light years away. Without lensing, their light would be too faint. With it, the black hole's gravity gathers their light and delivers it to us, brighter and sharper. The darkness acts as a lens, and the result is wonder. The invisible becomes visible by bending light around itself. There is something quietly humbling about this. Black holes, often imagined as destroyers, become instruments of vision. They hide, yes, but they also reveal. They block, and yet they illuminate. They are paradoxes woven into cosmic fabric. Every lensing event is like a reminder that the universe is not only violent but also generous, offering us glimpses of beauty through the strangest of means. In 1919, during a solar eclipse, the bending of starlight was observed near the Sun itself, a small taste of what black holes would later show on grander scales. That eclipse confirmed Einstein's theory, proving that space could bend light. Decades later, black holes revealed the full extent of this truth. They turned theory into spectacle, invisible giants bending light into arcs of elegance. And as these natural lenses magnify the distant past, they also reveal the present, that galaxies themselves are shaped, sculpted, and held together by black holes at their centers. Seeing the invisible through warped light, the irony of black holes is that while they themselves cannot be seen directly, their presence is revealed most vividly through light they distort. A star flickering oddly, a galaxy twisted into a ring, a quasar doubled in the sky. Each is a signature left by the unseen. We do not observe black holes directly, we observe the universe reacting to them. Their invisibility is not silence, but a chorus sung by light, bent to their will. This is how the first images of black holes came to us, not by photographing the hole itself, but by capturing the glowing ring of bent light around it. The famous image of the supermassive black hole in the galaxy M87 showed us not a black dot, but a shadow encircled by fire. The black hole itself remained hidden, yet its presence was undeniable. Light testified for it, bending, circling, obeying gravity's command. These warped visions are not only beautiful, they are evidence. They prove that black holes are not myths but realities shaping the universe. Each distorted light path is like a fingerprint, unique and unmistakable. Even when hidden, the giants declare themselves through the bending of what surrounds them. We cannot see their faces, but we can read their shadows in the curves of starlight. There is a deep lesson in this. Sometimes the most powerful forces are not seen directly, but known by their influence. Just as gravity shapes your steps without you noticing, black holes shape the galaxies without showing themselves. They remind us that not everything real must be visible. The unseen can be just as present, just as commanding as what shines in the open. And as we study these hidden giants through their warped light, we realize they are not rare curiosities. They are woven into the very structure of galaxies, standing silently at their hearts. Galaxies shaped by hidden centers. At the core of nearly every large galaxy lies a black hole, massive, ancient, and central. They are not guests in these galaxies, they are anchors. Their gravity sculpts the motion of stars, holds the spiral arms together, and even influences how galaxies grow. Without these hidden centers, the cosmos as we know it would not take the same graceful forms. Black holes are not outliers, they are architects. The Milky Way itself holds such a giant at its heart. We call it Sagittarius A, a black hole 4 million times the mass of our Sun. It sits quietly, usually unseen, yet every star in our galaxy feels its influence. The Sun's orbit, the spiral of arms, the flow of interstellar gas, all dance to rhythms set long ago by this hidden giant. Without it, our galaxy would be less stable, less complete. Supermassive black holes do more than hold galaxies steady. When they feed on matter, they release energy so intense it can shape star formation across their host galaxies. The jets of radiation they send outward can ignite or quench the birth of stars, depending on their fury. In this way, the hidden centers are also caretakers, guiding the life cycles of entire galaxies. Darkness becomes a shepherd of light. And this is perhaps the strangest truth. Black holes, known for consuming, are also creators in their own way. By sculpting galaxies, they give rise to the stars, planets, and life that follow. They do not simply destroy, they shape. They are woven into the story of existence, not as villains, but as silent partners, invisible yet indispensable. The monsters at galactic hearts. When astronomers first discovered black holes at the centers of galaxies, they were stunned by their scale. These were not the remnants of ordinary stars, but monsters millions, even billions, of times heavier than the Sun. They do not sit at the edges of galaxies, but right in their cores, like anchors sunk deep into cosmic seas. They are the giants that rule silently, holding entire galaxies in their grip. The word monster may sound harsh, but it captures the awe these objects inspire. Their size defies comprehension. Imagine a black hole so massive that its shadow would stretch wider than our entire solar system. Around it, stars orbit like moths around a hidden flame, moving at impossible speeds to avoid falling in. These are not quiet leftovers of dying stars, but colossal rulers shaping galaxies from within. And yet, despite their terrifying size, these monsters are quiet most of the time. They sit dormant, invisible, only revealing themselves when matter drifts too close. Then their true nature awakens. Gas, dust, and sometimes even stars are drawn inward, and as they fall, the black hole reveals its hunger. It is in these feeding frenzies that the monsters roar, not with sound, but with light brighter than any star. The presence of such giants tells us something profound. Galaxies and black holes grow together. The mass of a black hole and the size of its galaxy seem linked, as though their fates are tied. Perhaps the galaxies feed the monsters, or perhaps the monsters shape the galaxies. Either way, they are partners in the cosmic dance, inseparable across billions of years. And as we picture these galactic monsters, we must ask, what happens when they feed? What does it look like when a silent ruler awakens in hunger? The answer lies in the bright disks of falling matter glowing like cosmic whirlpools of fire. Supermassive black holes older than time. Some black holes are so ancient that they may date back to the dawn of the universe itself. Less than 1 billion years after the Big Bang, astronomers have found quasars powered by supermassive black holes already weighing billions of suns. How could something so huge form so quickly? The question unsettles even the most confident scientists. It suggests that black holes are not only monsters of the present, but fossils of creation itself. To find these ancient giants, astronomers look deep into the night sky. The farther we look, the older the light we see. In those faint, ancient glimmers, we find galaxies already anchored by massive black holes. The implication is staggering. Black holes may have been present almost from the very beginning, shaping galaxies as soon as galaxies existed. They are not late arrivals to the universe. They are part of its first architecture. This mystery raises possibilities. Perhaps the earliest stars, far more massive than today's, collapsed into black holes that grew quickly. Or perhaps black holes were born directly from collapsing clouds of gas, skipping the step of stars entirely. Some even wonder if primordial black holes, tiny ones formed in the chaos of the Big Bang, merged and grew into the supermassive titans we see today. Whatever their origin, their age ties them to the deepest questions of cosmology. And when we call them older than time, it is not just poetry. These black holes outlast civilizations, outlast stars, and perhaps outlast the galaxies themselves. They are cosmic elders, witnesses to billions of years of change. They remain silent and steady, even as everything else transforms around them. In their shadows we glimpse not just mystery, but endurance. And as we marvel at their age, we see how they live, how they consume, how they turn falling matter into glowing storms of fire and energy, feeding on clouds of gas and dust. When matter drifts near a supermassive black hole, it rarely falls straight in. Instead, it spirals, forming a disk of gas and dust spinning at tremendous speeds. This disk is heated by friction, glowing so brightly that it can outshine the galaxy around it. The black hole itself is invisible, but the feeding disk reveals its presence in dazzling display. Darkness becomes framed by fire. Picture a whirlpool in a river. Leaves and twigs swirl faster as they near the center, drawn toward the plunge. The accretion disk of a black hole is much the same, only with matter heated to millions of degrees, glowing across the spectrum of light, from visible rays to powerful X-rays. To telescopes, these disks are like cosmic lanterns guiding us to places otherwise hidden in the dark. These feeding events are not gentle. Matter collides, compresses, and is torn apart by tidal forces. Gas clouds fall in and are shredded, releasing bursts of energy before being swallowed. Even entire stars can wander too close, meeting violent ends that illuminate the darkness. The black hole consumes, but in its consuming, it also creates light. It is the paradox of destruction that reveals beauty. Scientists study these feeding frenzies to understand how black holes grow and how galaxies evolve. The energy released can heat surrounding gas, halting star formation, or push winds outward that sculpt the galaxy. A single black hole's meal can influence billions of stars. This connection between feeding and shaping shows us that black holes are not isolated. They are deeply entangled with the life of their galaxies. And from these glowing disks of matter, sometimes even more dramatic sights emerge, jets of radiation bursting outward like cosmic lighthouses shining from the mouths of darkness, the bright disks of falling matter. Accretion disks are among the brightest phenomena in the universe. In some cases, they shine thousands of times brighter than entire galaxies. From Earth, they appear as brilliant points of light called quasars, visible across billions of light years. Imagine something so far away its light began traveling before Earth even existed, yet still so luminous it reaches us clearly. That is the power of matter falling into a black hole. The disk glows because of speed and heat. As gas and dust spiral inward, friction turns them incandescent. Atoms collide at near-light speeds, releasing enormous amounts of energy. What began as cold, drifting gas becomes a furnace bright enough to be seen across the cosmos. The black hole itself remains unseen, yet its meal lights up the universe in testimony. It is darkness announcing itself with brilliance. This brightness can last for millions of years, though it is not constant. Feeding comes in bursts, quiet times interrupted by frenzies. When the disk is full, the galaxy shines with unusual brilliance. When the meal is over, the glow fades. In this rhythm of feeding and resting, galaxies pulse with life shaped by their hidden cores. The light of quasars is, in a way, the heartbeat of the universe. For astronomers, these bright disks are both a beacon and a puzzle. They allow us to study black holes at immense distances, but they also raise questions. How do black holes grow so fast? How do they power jets of particles stretching far beyond their galaxies? Each glowing disk offers clues but also deepens the mystery. They are not just light shows but invitations to wonder. And as we watch these luminous whirlpools, we notice something stranger still. Though black holes swallow light, their feeding often produces radiation that escapes, making the darkest places paradoxically glow. Radiation bursting from invisible mouths. From the edges of accretion disks, enormous jets of particles shoot outward at nearly the speed of light. These jets can stretch for thousands of light years, piercing through the darkness like cosmic lances. How can something designed to swallow everything also release such spectacular streams of energy? The answer lies in the magnetic fields and furious rotation of matter swirling near the black hole. The very act of falling creates escape in the form of radiation. These jets are among the most powerful engines in the universe. They release more energy than millions of stars combined. Galaxies with active black holes blaze with these outflows visible to our telescopes across unimaginable distances. The black hole itself remains hidden, but the jets scream its presence, carving paths through intergalactic space. Silence at the core gives rise to thunder far away. Scientists still debate the details. Perhaps the spinning disk winds magnetic fields into tight coils, launching particles outward. Perhaps the rotation of the black hole itself drags space-time and fuels the jets. Whatever the mechanism, the result is a paradox. Black holes, known for trapping light, become sources of immense brightness. They are mouths that consume, but also mouths that radiate, glowing not from within, but from the energy of what they devour. The impact of these jets is profound. They can heat entire clusters of galaxies, regulate star formation, and shape cosmic environments across millions of light years. In this way, black holes do not only feed, they also give back, redistributing energy across the universe. They are sculptors, balancing creation and destruction in equal measure. Their hunger shapes the galaxies not just by consuming, but by illuminating and transforming what lies around them. The paradox of darkness that glows, it feels like a contradiction, doesn't it? A black hole, defined by its ability to swallow light, becomes surrounded by the brightest phenomena in the universe. This paradox is at the heart of their mystery. Darkness consumes, yet in the act of consuming, it creates brilliance that can outshine billions of stars. It is a silence that produces music, a shadow that paints fire across the sky. This glow does not come from the black hole itself, but from the matter just before it vanishes. Gas and dust spiral inward, heated to extraordinary temperatures, releasing radiation that escapes before the final plunge. In that last moment of freedom, matter sings its brightest song. The black hole's darkness is framed by this final outcry of light. The paradox is haunting. To stand at the edge of such a place would mean seeing both extremes at once. Absolute darkness at the center, surrounded by furious brilliance. It is like watching the end of everything and the birth of wonder in the same instant. The universe seems to say that endings and beginnings are never far apart. Even in consumption, there is revelation. This glow reminds us that black holes are not dead ends, but dynamic participants in the cosmos. They do not only erase, they also create signals, patterns and energy that ripple across galaxies. Their paradoxical nature is what makes them so compelling. They are not simply dark, not simply destructive, but woven with contradictions that challenge the way we define reality. And nowhere is this paradox more vividly seen than in quasars, those distant, ancient beacons powered by the hunger of black holes, quasars as beacons of the deep past. A quasar is what happens when a supermassive black hole feeds with ferocity. The accretion disk glows so brightly that it drowns out the stars around it, turning the galaxy's heart into a cosmic lighthouse. Some quasars shine with the energy of 1 trillion suns. They are so luminous that we can see them from the farthest edges of the universe. They are beacons from the deep past, their light carrying messages billions of years old. When we look at a quasar, we are not just seeing brightness, we are peering into history. The light we capture tonight may have begun its journey before Earth even existed. It traveled through eons across expanding space to arrive at our telescopes. Each quasar is both a lamp in the dark and a time machine, letting us glimpse the universe when it was young and chaotic. Quasars are powered by black holes, millions to billions of times more massive than our Sun. Matter falls into their disks, heats up, and unleashes energy so extreme that it can be detected across the entire cosmos. From Earth, they appear as small points of light, yet behind that point lies a black hole devouring galaxies' worth of matter. It is a scale that makes even our Milky Way seem small. The beauty of quasars lies not only in their brightness but in their endurance. They burn for millions of years, steady and unyielding. In their glow, we see the hand of black holes shaping galaxies long before our own Sun was born. They remind us that the universe has been alive with drama since its earliest moments, and that black holes were central to that story. And as we follow their light across time, we begin to see how these ancient signals teach us about the very growth of black holes and galaxies together. Ancient signals from billions of years ago. Every quasar we see today is an ancient messenger. Its light began the journey long before life on Earth arose, long before even the Earth itself formed. Looking at them is like opening a window into deep time. The faint glimmer of a quasar is not just a distant shine, it is the voice of the universe speaking from billions of years in the past. These signals show us how galaxies and black holes evolved together. By studying quasars at different distances, astronomers can trace how black holes grew, how galaxies formed around them, and how their fates have always been linked. It is like watching a series of snapshots across cosmic history, piecing together the growth of the universe frame by frame. What is remarkable is not just the distance, but the clarity. Even though the light has traveled for billions of years, it still carries with it the signature of the black hole's power, bright disks, radiation, and jets stretching into space. The past has not faded, it shines in our present with unwavering brilliance, a reminder of how vast and enduring the universe truly is. There is a humbling effect in this, to realize that when the first quasars lit up, our galaxy was not yet formed, our Sun was not yet born, and Earth was not yet imagined, and yet their light waits for us patiently, arriving in the moment we are ready to understand it. They are reminders that the universe holds its memory in light. And from these memories, we learn that the growth of black holes and galaxies is not separate. Their histories are braided together as if one cannot exist without the other. The growth of black holes with galaxies. For decades, scientists wondered, do galaxies create black holes or do black holes create galaxies? The truth appears to be both. They grow together, each shaping the other. Observations show that the mass of a galaxy's central black hole is linked to the size of the galaxy itself. It is as if the black hole and the galaxy are partners, born together, living together, and aging together. The black hole feeds on matter from its galaxy, pulling in stars, gas, and dust. In return, its energy outbursts regulate how many new stars the galaxy can form. Too much energy, and star birth slows. Just enough, and the galaxy thrives. This delicate balance suggests that galaxies and black holes co-evolve, locked in a cosmic feedback loop. The darkness at the core is not separate from the light of the stars. It is a partner in their growth. We see this pattern everywhere. Tiny galaxies host smaller black holes. Giant galaxies host monsters billions of times the sun's mass. The relationship is consistent, hinting at a law of nature we do not yet fully understand. It is like seeing families where the child and the home always seem to grow in step, each shaping the other's destiny. The black hole is the hidden parent, quietly guiding the galaxy's story. This growth is not always smooth. Galaxies collide, merge, and their central black holes do the same. In these moments, growth accelerates and new structures emerge. The cosmos is not a still picture. It is a living drama with galaxies and black holes as the main actors. And in this drama, their relationship shapes the very map of the universe. And so we realize that nearly every galaxy, including our own, carries a black hole at its core. They are not strangers to each other. They are companions bound from birth to the end of time. Why every galaxy seems to have one. The more astronomers looked, the clearer it became. Black holes are not rare oddities. Nearly every large galaxy we study carries one at its center. From small spiral galaxies like our Milky Way to giant ellipticals, the pattern holds true. It is almost as if black holes are not exceptions, but requirements for galaxies to exist at all. They are the hidden hearts beating at the center of cosmic cities. This discovery shifted how we think about the universe. Black holes are not just dangerous curiosities lurking in shadows. They are essential parts of galactic life. Without them, galaxies might not hold together, stars might not form as they do, and cosmic structures might lack their balance. The invisible centers are as important as the shining arms of stars that orbit them. The Milky Way is no different. At its core lies Sagittarius A, a black hole 4 million times the Sun's mass. It is quiet compared to the raging quasars of the distant universe, but its presence is undeniable. Stars near the center move at incredible speeds, circling an unseen mass. We cannot see the black hole, but the orbits of stars testify to it. It is the silent ruler of our home galaxy. Knowing that every galaxy carries such a heart changes how we view the cosmos. It suggests that black holes are not rare accidents but universal companions, present wherever galaxies rise. Their story is not separate from the story of the stars, but central to it. The darkness at the core is as natural as the light that fills the arms. The dance of binary black holes. Sometimes black holes do not live alone. They come in pairs, circling one another in a slow, majestic dance. Imagine two invisible giants locked together, each pulling at the other, spiraling closer with every orbit. This is the reality of binary black holes. They are rare to see directly, but their presence is written in the movements of stars and the ripples they send across space-time. Their dance is one of the most powerful phenomena the universe knows. The idea of two black holes bound together may seem impossible, two bottomless pits sharing one gravity well. Yet nature creates them when galaxies merge, their central black holes drawn into orbit around one another. What follows is a courtship lasting millions of years. With each orbit, energy is lost, not through light, but through waves in space-time itself. Slowly, silently, the partners draw nearer, their dance tightening until they collide in a final embrace. This dance is slow on human scales, but on cosmic scales it is dramatic. Imagine watching two stars orbiting something unseen, their paths twisting in ways only explained by twin black holes. For astronomers, these pairs are like hidden orchestras, unseen directly, but their rhythms can be measured. The invisible giants leave their footprints in the cosmos if one knows how to look. The spiraling dance of binary black holes reminds us that even in darkness, relationships form. Nothing in the universe is fully solitary. Even black holes, with their immense gravity, are drawn toward one another, compelled into companionship. And in their dance they create something extraordinary, waves that ripple across the very fabric of reality. And so as we imagine these silent partners circling in darkness, we begin to hear the faintest music of the cosmos, carried not by sound but by space-time itself, spiraling closer in endless embrace. The dance of two black holes is not static, it is a spiral. Each orbit brings them closer, each turn releases energy into the cosmos. Over millions of years their distance shrinks and the spiral tightens like a thread winding on a spool. Their embrace is inevitable, but the path toward it is long and graceful. To picture it is to imagine two whirlpools circling closer, the water between them flowing faster until they merge into one. This spiraling is not visible to our eyes, but its consequences are profound. The energy released as they orbit escapes in the form of gravitational waves, ripples spreading outward through space-time. These waves carry away the system's energy, shrinking the orbit little by little. The spiral continues, silent but unstoppable. What looks like endless circling is actually the slow preparation for a dramatic collision. It is humbling to think of the scale. These black holes may orbit one another for millions of years, each orbit lasting days or hours, until at last, in the final moments, they whirl around each other dozens of times per second. The spiral accelerates into a furious dance, faster than anything we can imagine, ending in a union of unimaginable force. Yet through it all, no light is seen, no sound is heard, only the invisible ripple of reality itself. To us, their embrace is silent. To the universe, it is thunder. The spiraling motion becomes a beacon not of light, but of gravity itself. It is as if the cosmos whispers through waves rather than words, announcing the union of giants in vibrations that pass through everything. And when they finally collide, the spiral ends in a single black hole, larger than before, its silence deeper, its gravity stronger. Yet the ripples they leave behind travel across billions of years, eventually reaching us, faint but unmistakable. The silent waves they send through space, gravitational waves, are one of the most delicate yet profound discoveries of modern science. Imagine space-time itself as a vast pond. When two black holes spiral and collide, they send ripples across this pond. These ripples stretch and squeeze everything they touch, though so faintly that even the most sensitive instruments barely detect them. They are silent waves carrying stories of cosmic events across the universe. These waves are not like sound or light. They are distortions of space itself, moving at the speed of light but carrying information in an entirely new way. For centuries, humanity relied on telescopes to see the universe through light. With gravitational waves, we now listen to the universe in a different voice. It is as if the cosmos has opened another channel, whispering secrets we could never hear before. The signals are tiny. A passing wave might stretch the distance between Earth and the Sun by less than the width of a human hair. And yet, with instruments sensitive enough, we can measure it. This feat is almost unbelievable, detecting vibrations in space-time itself caused by black holes billions of light-years away. It is science that borders on poetry, precision that feels like magic. And what do these waves tell us? They confirm the existence of black hole mergers. They reveal the masses of the colliding giants, the speed of their spirals, the very moment of their union. Each wave is a record, a cosmic memory carried across the void. By listening to them, we hear events we could never see, unfolding in galaxies far beyond our reach. These silent waves change our relationship with the universe. For the first time, we do not only watch the cosmos, we listen to its vibrations. It is as if we have grown a new sense, one that lets us feel the heartbeat of creation itself. Ripples that stretch and squeeze reality. When a gravitational wave passes, reality itself distorts. Distances stretch one way, then squeeze the other, like the rhythm of breathing. Imagine a ruler 1,000,000 kilometers long. During a wave, its marks shift ever so slightly, expanding and contracting as space-time ripples by. This is not metaphor, it is real. Gravitational waves reshape the stage on which all things exist, reminding us that space is not rigid, but alive with motion. The effect is unimaginably small, but the fact that it exists at all is astonishing. Black holes colliding billions of years ago can send ripples strong enough to reach us today. Those ripples pass through galaxies, stars, and planets unnoticed until they brush against our instruments. We live inside these ripples, yet they are too subtle for our senses to feel. It is like being in the middle of an ocean, unaware of the waves beneath the surface. Detecting them requires machines of exquisite sensitivity. LIGO, for example, uses lasers to measure distances with such precision that it can detect changes smaller than an atom's width. When the first ripple passed in 2015, the instruments quivered and history was made. Humanity had, for the first time, felt the stretching and squeezing of space-time itself, caused by the collision of two black holes over 1 billion years ago. This discovery is more than scientific, it is existential. It reminds us that we are connected to events unimaginably far away. Every ripple that passes through us is a greeting from the cosmos, a signal of something vast and powerful happening in the darkness. We are not isolated, we are touched constantly by the movements of the universe itself. And as we reflect on this, the story of Einstein's prediction comes alive, a vision he offered a century ago, finally proven by trembling mirrors catching ripples in space-time, how we finally detected those waves. For 100 years, gravitational waves were only theory. Einstein predicted them in 1916, but he doubted we would ever measure them. They seemed too faint, too elusive, lost in the background of the universe. And yet, a century later, we built the instruments sensitive enough to catch them. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, recorded the first signal. Two black holes had merged, sending ripples that stretched across space-time, reaching Earth after traveling more than 1 billion years. The detection was a triumph of patience and precision. LIGO works by splitting a laser into two beams, sending them down long tunnels, and reflecting them back. When a gravitational wave passes, the beams stretch and squeeze ever so slightly, changing their pattern. The shift is smaller than a proton, yet it was enough. The universe whispered, and our instruments heard. That first signal was not just data, it was a cosmic story. It told of two black holes, each about 30 times the mass of the Sun, colliding in a distant galaxy. The energy released in that instant was greater than all the light from all the stars in the observable universe combined. And yet we felt it here, on our small planet, as a subtle ripple in space-time. The discovery confirmed Einstein's vision and opened a new era of astronomy. No longer bound to light alone, we could now listen to the universe. Each detection since then, mergers of black holes, neutron stars colliding, adds to the symphony. Gravitational wave astronomy is young, but it is already reshaping how we see the cosmos. We are not only spectators of light, we are listeners of space itself.